Okay. But we are going to today we are going to study other type of series. Okay, let's look at this following problem first. So if n starts from 1 to infinity, 1 of n, right? We know that this is divergent. Okay, it is divergent. How do you prove it? It's divergent. The easiest way, okay, to prove it's divergent, that probably is the only way you can prove it's divergent. No, the easiest way to prove divergent is using the integral test. Okay, it's divergent since integral from 1 to infinity, 1 of x dx is going to be, right? It's easy to check. It's going to be infinity. Okay, we use the integral test. Okay, and how about I change the sign? Okay, okay, this could be 1 over n. Okay. This is called, it is called alternating series. Okay, alternating series. Okay, then I have no idea, you know, I have to be very careful to to study that, right? Is it divergent or convergent, right? I know the nth term convergent is 0, but that's not guaranteed. Okay, this is the n. Okay, I note that the limit n approaches infinite is going to be 0. But this does not guarantee this series is convergent or divergent. You cannot say that's convergent. So when I grade your home a quiz or test, even your answer, so-called answer, is correct, say it's convergent, but you cannot get credits because you did not, your argument does not support it. You use the wrong argument to prove it's divergent, it's convergent. Okay, so you cannot, you only observe that the nth term approaches 0. You know, and here is this, right? If they approach 0, it's clear. So maybe I give it 2 points out of 10, but I cannot give you the credit. Okay, so you have to find the right method to prove that. Of course, we're going to learn a method called alternate series test. But before do that, suppose you never learned this as a mathematician, right? How do you study that, right? So you have to look at the partial sum. Okay, the partial sum, I'm going to use 2k here. Okay, partial sum is going to be so 2k. You know, you have to list them pair by pair. Okay, so when n equals 1, it's 1 over 1 and 1 over 2, right? Plus 1 over 3, and then 1 over 4. Okay, and you can concede as 2k minus 1 minus 2k. And look at this. This is going to be, each term is non-negative. Okay, each term is going to be non-negative. So this series, is going to be a series of, if you regroup them, this is going to be the sum of non-negative terms. Okay, it's positive terms. Okay, and maybe you can prove that it's convergent. Why it's convergent? You can regroup them, right? Every term, yeah, this is a regroup them. You know, if it's pair, right? So this pair, if you look at the growth rate, okay, it's going to be 1 over square type. Okay, look at the last term. Combine them, it's 2k minus 1, 2k, then 2k minus 2k minus 1. So the numerator is just 1, 2k minus 1, and 2k, right? And then this is almost equal to 4k squared, right? So it decays pretty fast, right? So if you call this one B1, that's a big, you know, yeah, this is the first term. The second term is called B1, B2, and then I think this will be BK, okay? When K equals 1, I get the first one, okay? Then S2K is just sum of the Ki start from 1 BI. And you actually convert this alternative series to series with positive terms, okay? And then BK is gonna be 2k minus 1 2k, right? It's almost equal to 4k squared, 1 over 4k squared. So clearly, this is convergent. We know that it's convergent. Okay. This is a convergent. Why? By the limited comparison test, because you can compare with that one. Okay. So in other words, when K approaches infinity, this is going to be it's a finite. Okay. All right. And then all right, so this means S2K is going to be, right? So how about SK minus 1? S2K minus 1, because you only consider the sum of even terms from 1 to 2K, but from 1 to 2K, let's say other term, 2K plus 1. 2K plus 1 is 2K plus the last term, which is 1 over 2K plus 1, okay? Addition term. But if this is convergent, then the second term approaches 0. So that's why the limit of K approaches infinity, 2K minus plus 1 is going to be the limit of, okay? Fine. So that implies, this implies the limit Sn is convergent. Okay? Okay. All right, so this, and what is the limit? I think, yeah, the value, we don't know the value exact. Okay. We can, well, this particular case, you probably can get the values because this sigma, no, sigma b is not. They cannot cancel. Yeah. Okay, so we only know it's convergent. Okay, the biosimilar ideas, there's another way to check whether this is convergent without using the specific value. Okay, you can also check that. Let's see, how can I see this is a convergent? Let's go back to, you know, I use the special case. Okay, so let's go back to this one. It's going to be 1 over 1, right? 1, 2, 1 over 3, right? Minus 1 over 4. And 2K minus 1 minus 2K. If I regroup them in this way, okay, and so on that term, okay, then this is always negative, right? If you regroup them in this form. So this is going to be less than or equal to 1 over 1 minus 1 over 2K. So this is the upper bound, right? I know S2K because the sum of all the positive terms is increasing. But I also know that S2K is less than or equal to 1, okay? Because when I regroup those terms, and that means okay, this K goes to infinity, is convergent, okay, exists. Okay. So that's another argument, yeah, to show the limit of S2K exists. Okay, but this is can be used for more general alternating series. So let me state the theorem. Let me state the theorem. Okay, we consider an alternating series. This is a negative n minus 1 Bn. It can be in a more general form. Okay, so Bn is positive. Bn is decreasing to 0. Then this series is convergent. Then the series, this series is convergent. The argument is already, the idea is already given for the above specific problem, so I'm not going to prove. Okay. All right. So now let's look at some examples. Let's take a look at the following example, the first example. Then start from 0. Yeah, so the theorem state, it's not necessarily n start from 1, n start from any capital N, okay? I modify a little bit. So like in this example, n start from 0. So the convergence is independent of the finite terms at the very beginning. Okay, take a look at this. This is not in the same format, right? But you can change that. You can change that. It's going to be minus 2 to negative n minus 1 divided by, okay? It's the same. Then Bn, you take a look at the square Bn, right? Then this is clearly positive, decreasing to 0. Obvious. You don't need to prove that. So this implies the series is convergent. By the alternating series test. Okay, it's called alternating series test. You have to say that. However, without the negative sign, this is divergent. You know why it's divergent? You compare with the P series, okay? And it's the P series is this is n. It's almost equal to this, which is n to the 1/2. That's Bn, right? So Bn is the sigma Bn is divergent because P is equal to 1/2, which is less than 1. And then by the limited comparison test, the sigma n is also divergent. Okay, first of all, we know that this is divergent. Why? You have to say that by the P series test was P equals 1/2, which is less than 1. Right? Then this implies this is divergent by the limited comparison test. Okay, why? Because the limit and Bn is going to be 1. Right? Yeah. It's guaranteed, it's always 1. If you drop the unnecessary lower order terms, the limit is always equal 1. Okay? Right. Okay, so the argument is this is complete, so you will get 4 credits if you can show all the details, not just say claims divergent. You have to explain why it's divergent. Okay, so we give a credits not to answer, we give a credits to the solution. Solution consists of the arguments and the answer. Okay, there's a big difference between solution and answer. Yeah. Right. Yeah, here's an interesting problem. Q number is problem. N square plus n plus 1. All right. So think about, I'll give you a half minute to think about it. Make a conjecture whether it's convergent or divergent. Divergent or convergent? No idea. How about you? Not sure. It's alternating series, but you cannot use alternating series test to prove it's convergent. Okay, so look at the Bn. No, okay, so here's n. N is okay, n minus 1, n doesn't matter. You know, you can write, if you really want to take the negative sign out, you know, then you get something like that. So the Bn. Bn is n square plus n plus 1. But this positive, no problem. But Bn convergent to 1, not 0. Okay? Yeah, it's convergent to 1 is obvious. N squared is the numerator, n squared is the denominator. Okay? So Bn convergent to 1. So you cannot use the alternating series test to prove the series is convergent. Okay? But you cannot prove that using alternate series test to prove that it's divergent. No. So alternate series does not say that. Only says that under this condition, then the series is convergent. But if that condition is not satisfied, you can get nothing from alternating series test. Right? So you cannot use alternating series test to jump to the conclusion it is divergent. Okay. Yeah, this is it's called sufficient necessary condition or just necessary condition or sufficient condition. The theorem state in the alternating series test is a sufficient condition. Suppose that is true, then it is convergent. But recall that there's called nth term test. Nth term test is necessary condition state. If it's convergent, then what happens? Okay, so if, right, if the series is convergent, okay, remember, let's just state the general, okay, the series of n. If the series starts from any number, right, is convergent, okay, then the limit of n should be 0. Okay, this is called the nth term test. You can name it, right? Because it's talking about nth term. So our an is going to be negative n to the n square plus 1. The second, this fact converges to 1, but it's multiplied by n, negative 1 to the power n. So the limit n does not exist. Why does it not exist? Because it's jumped between almost between negative and positive. It does not approach a fixed number. That does not exist. If it does not exist, of course it's not going to be 0. Right? This statement says that the limit exists n equal to 0. Now, does not exist. So that means this implies does not hold. Okay? So therefore, you can say that series is divergent. Yeah. Okay. The series is divergent by the nth term test for divergence. The nth term test only works for divergence. Got it? So this is a correct argument. Then you become an excellent lawyer if you argue in the court like that. Okay. But as a jury, you can say, I feel he's guilty. That's it. You all need to say that. You don't need to argue, prove using any law. That's the difference. Yeah. Okay. Yeah, you have to mention that.
Well, like in the one before it, like if I said this term is greater and it's convergent, therefore the series given is convergent.
Well, I have to say by the comparison test or limited comparison test, you have to mention that. If you don't want to waste too much time to write it, just LM limited LCT. Yeah. Okay. Yeah, I'm going to finish all the even number problems, number 10. I think this is a convergent. I can see that. I don't need to check that. So it's convergent. So when you know it's convergence, so you have to just work in that direction. If you think this is divergent, then use the alternate, use the nth term test to prove it's divergent. Okay, maybe you can use as a test later on, but not right now. Okay, so this is why this is a convergent. Well, it's alternative series, first thing, right? So I look at the Bn. That doesn't matter. It's n minus 1 n. Okay. So Bn is going to be square n to n plus 3. I know it is positive. The question is whether it's decreasing to 0. That's the question. You have to prove it's decreasing, not only just converging to 0. You have to prove 2 things, 3 things. 1, 2, right? Bn decreasing. 3, Bn the limit converging to 0. You have to prove 3 things. I think converging to 0 is obvious. Just like the integral test. Sometimes you see the function. Yeah, you don't even check if it's converging to 0 now, because in that case, but you have to prove it's divergent. It's decreasing, yeah, it's decreasing. So this is obvious. Yeah, n approaches the infinity. It's going to be 0. This is how do you see that? You just divide by n. So it's 1 over square n, and 2 plus 3 over n. Okay. And this is going to be, the numerator is going to be 0, denominator 2 plus 0. That's a 0. Okay. Okay. So let's prove this decreasing. In order to prove decreasing, you have to look at the function. Only use a function, and then f of x is square of x, 2x plus 3. Then you can differentiate, okay? So you differentiate. You want to prove it's negative for large n. 2x plus 3 squared. The derivative of square of x, okay, minus square of x times the derivative of 2x plus 3 is 2. Okay, you have to simplify. Take a square out. I move that 2 square of x down. Okay. So I got 2x plus 3, no problem, minus, I have a 2 square x, 2 square x is 4x. Okay. So you get 3 minus 2x. All right, and is going to be negative? I think so. For large x, the numerator is going to be negative. So this is going to be negative if x is greater than 3 over 2. Okay? Yeah, that's all, you know, x, the function looks like that. X, yeah, y, x's, it's going to be, here's a 1, this is 2. And when x equals 0, I think as a function goes up and goes down, like that. Okay? Yeah, this is a half of it. So really after 2, it's again going down. So that means Bn equals f of n, going down for n greater than or equal to 2. Right? Another one. It's possible B1 is still less than B2. Okay? B1 is still less than B2. But after B2, they all, you know, B2 is greater than B3, greater than B4. Okay? Yeah. All right, that's all we needed. Okay. Then you conclude that this series is convergent by the alternating series test because you verify all the required conditions. Okay. Yeah, this problem is different from other problems. It's not obvious. This sequence is Bn is decreasing. It's not obvious. You have to prove that. And there's problems too, you know, like a problem number 12. It's negative n plus 1. Okay. All right, so our Bn is going to be n e to the n, so it's going to be n. And when I look at, okay, when I write in this form, I say clearly this is going to be convergent. Why? Because it's positive, right? So first of all, Bn is positive, no problem. Bn decreasing. That's a question. This is a question, right? And 3, Bn converging to 0. I think that's obvious. Why? Because the exponential function grows faster than the polynomial. So the ratio will decrease, will be decreasing, okay? But you can check that direct, right? So you look at the function x e to the x, then your derivative of the function is going to be 1 times e to the x minus x times e to the x. So you take, it's 1 minus x e to the x, and clearly it's going to be negative if x is greater than 1. Done. Okay, so this implies f of x decreasing on the interval from 1 to infinity. So this implies yeah decrease. Okay. Then you can conclude that the series is convergent by the alternative series test. All right, here's another question I want you to think about, problem number 14. Let's push through this problem. It's convergent or divergent? Okay, divergent. Okay, so the reason it's divergent is because you should know that this is going to be pi over 2, right? Yes. So it's going to be pi over 2, so it's not going to be 0. So this implies this does not exist. Okay? If you, yeah, this does not exist. Okay, it's definitely not going to be 0. Okay. Yeah, the second part converging to pi over 2, but the first part is alternating. You know, it changes sign. So this limit does not exist. Therefore we get, yeah, we do. So then this, we should say the series, okay? Not just, don't just say it was. Yeah, the series is divergent by the nth term test. Okay. We have two problems here. I think the second one, it's difficult to do it here right now, but we are going to study that late. Okay, in the next. Okay, so look at the difference between those two. The tiny bit difference here. Here's cosine n pi. Here's just cosine n. Okay. But cosine n pi essentially is you can evaluate. So cosine n pi just n, it's just a negative sign, depends on the value of n. So when n equals odd number, it is going to be a negative. When n is even number, it's going to be positive cosine. 2 pi is positive 1. So that's what you get. Then it's easy to check. So Bn equals n over 2 to the n. I have to make sure 1, it's positive always. 2, this is decreasing. 3, the limit is going to be 0. Okay. Now decreasing, it's almost obvious because the denominator is the exponential function. The numerator is a polynomial. But it's better to give a simple proof. You just look at the function f of x equals x over 2 to the x, right? Then you differentiate. If this function is decreasing, then the sequence is decreasing. Okay, so this is a derivative, 2 to the x square, and derivative of x is 1, and 2 to the x minus x. The derivative of this is going to be natural over 2 times 2 to the x. So I get 1 minus natural log of 2 times x. When it's going to be negative, it's going to be negative if x is greater than 1 over natural of 2. So we don't know the exact value of natural log of 2. I have to do some rough estimate. But anyway, 1 over natural log of 2 is a positive number. It could be 10, right? So I think this is a true if x is greater than 10. Let's pick a larger number. And I'm pretty sure this 10 is greater than 1 over natural log of 2. Okay? And now, of course, guarantee this derivative. So that means Bn decreasing to n greater than or equal to 10. That's enough, right? Okay, so we're done. So this implies sigma. That is, Bn is convergent. Yeah. Our Bn is n over 2. Yeah, it's convergent by the alternating series. Now, question. Yeah, this is the question. How do you know this is a lesson, right? Nature of 2. I'm trying to think about. I know E, E is a good number, right? E is going to be 2.7. Okay. I have to find the lower bound for the 2. Okay. So 2 is greater than, cannot greater than e. How about greater than square root of e? That's true. Because when you square it, 4 is greater than e. Yes. Okay. So that implies natural log of 2 is greater than natural log of square root of e is going to be 1/2 natural log of e is going to be 1/2. That's okay. It's possible. Okay. So that means natural log of 1 of natural log of 2 is less than or equal to 2. So 2 is enough, actually. Yeah, of course, less than 10. Okay. All right. But the other problem, if I just ask you to consider this, this is convergent, but we cannot I cannot use any method here to prove it's convergent. Okay, it changes signs, but changes sign in some strange way. Cosine n changes signs, yes, but it's not like alternate. Yeah, cosine n does change signs. Okay, but we're not going to use that property. We can use the property of a pseudo of cosine n is less than equal 1 to prove it's convergent. Okay, so we're going to prove it in the next class. We will prove the convergence in the next class. Okay, we cannot prove it right now. So it's not an alternative series. Cosine n is not going to be -1 to pi. All right. How about the next problem? I have a cosine pi over n. Another one is cosine pi over n. All right. Which one is convergent? Or both are convergent? Can you just quickly say that? The first one on the left, convergent? Could be. You have to prove it, whatever you click. Ah.
There's 5 under 0, cosine 0, 1.
Yeah. Yeah, that's right. Okay, so first of all, you consider the first one, right? So cosine pi over n goes to cosine 0, which is what? Sine pi over n goes to sine 0, which is 0. That makes a bigger difference. Okay, so clearly the first one is divergent. So if n equals negative cosine pi over n, then the limit n does not exist. Okay, it's not going to be 0 definitely. Okay, so that's why this implies pi over n is divergent. Okay, by the nth term test. But the other one is convergent. The reason it's convergent is you look at Bn equals sine pi of n. Okay? And it's decreasing. Okay? So Bn is positive for large n, and Bn is decreasing for n greater than or equal to 2. Okay? Okay? And then it is going, the Bn approaches 0. So why Bn is greater than decreasing after n greater than 2? The reason is it's when n greater than or equal to 2, the angle is between 0 and pi over 2, and the sine, the derivative of the sine become cosine. It's positive. Wait a minute. Wait. So it's decreasing. Okay. Now why it's decreasing, right? Yeah, look at the picture here. I just explain the picture. This is a sine curve, and this is a pi over 2. So that's why I need a pi gradient. So when this is a pi over n, right? And clearly, when n is increasing, the corresponding sine value decreases too. Okay, that's obvious. Okay, so then therefore this implies it's convergent by the alternating series test. But if it removes up the negative sign, it is going to be divergent. Okay, so let me put a remark here. This is still divergent. Why? Why it's divergent? Come. No. But you have to prove why it's goes to infinity. But clearly it's positive all the terms, right? Think about what you can do. You already learned integral test. You learned integral test, you learned the comparison test, limit comparison test. You can prove that using integral test. Honestly, you can prove that use a comparison test or limit comparison test. Let's do both, okay? Prove. F of x equals sine pi. Let's use x here. I'm not sure you can use the integral test. This is 1 of x, okay? And x, let's look at on the interval, okay? On this interval, f comma x equals differentiate cosine pi of x. Okay, and this is clearly it's going to be negative. So that means f of x decays. Okay. So if f of x decays, then you can apply the integral test right here. So you have to evaluate this this integral. Now the problem is, can you evaluate? It's not easy. You may try to use substitution. Okay, let's look at just find the antiderivatives. Okay, and use substitution lets you to be it just change it, just pi of x. Okay, so I get sine u. And the dx, when you differentiate, du equals negative pi x squared dx. As you see that, we are getting some troubles here now. Right? And pi x squared is going to be u squared. So x squared here is going to be pi squared and u squared. So you have to evaluate the integral. There's u and the sine. And that's almost impossible, I just say. Right? Not a good idea using integral test. So you have to make a choice. Okay? It's not a good idea, bad idea, right? So we see more options does not mean better. Okay? But you have to find the right tool from the toolbox to fix the problem. Okay? So when I look at this n, right, sine pi over n, right? I know it's almost, because sine x is almost equal to x for x is small. Right? That's a good part. So Bn, I'm going to use pi over n. Okay? Then I see that the limit as n approaches 0, and that is going to be 1. Right? It is going to be 1. This is because the limit as x approaches 0, sine x over x is going to be 1. Okay, right. So now you know what I'm doing. Use a limit comparison test. Okay. So, however, right, this is a divergent. Okay. Why it's divergent? It's harmonic series or the P series. P series. P equals 1. Okay. So it's divergent implies n is divergent. I think this is the easiest way to do limit comparison test. Okay. Let's do one more problem. All right, so this one clearly is convergent. All right, so this is a BN. I want to see if BN does not approach 0, then it's divergent. If BN is convergent 0, more likely it's going to be convergent, because most of the time it's always decreasing. Okay, so Bn equals to n plus 1, and how do you see it's converging to 0? It's a standard method. Okay, if you enumerate after squared, it's going to be n plus 1 minus n. Okay, which is just equal to. So you can completely change the expression. All right, so that's the same technique. So clearly, this is a clearly, I should clearly, then you don't need to find the derivative. It's not necessary. Clearly, Bn is decreasing, and clearly, this is going to be 0, right? Therefore, by the alternating series test, okay. Yeah. So for the alternating series, you can either use an nth term test to prove it's divergent, or use the alternating series test to prove it's convergent. Okay. So when you study, when I was a student, I usually do that. When I get home, first of all, I read the notes. Okay. I cover the solutions. I try to figure it out by myself. If you really couldn't do it, then I look at the notes. After go through this part first, then I started the homework. After finish the homework, I have a notebook, another special notebook that have key ideas. And for this section, I just write down 2 key ideas. One is for alternating series, okay? Look at the nth term. If the nth term does not approach 0, you use the nth term test to prove it's divergent. Otherwise, more likely, yeah, it's going to be convergent. Use alternating series. Just needed to use a derivative to prove it's decreasing. Something like just a couple lines. That's a note. Yeah, and then next time when you review it, it's yeah, you can quickly catch the idea. You don't need to redo lots of problems. Okay, so I usually have a 2 notebook. One is just taking notes in the classroom. But not like here. Early days, there's no emails even. No email, definitely. When I was graduating, only the last year, I got an email account. I can send the emails. And the memory is very low, cannot save lots of mails. No attachment, definitely. But it's already great communication, yeah. And yeah, also we only take notes but I also have another notebook, just keeps the key ideas. And then sometimes I put a key example there, so you can remember. Okay, you have to learn how to summarize that, no matter which course you're taking, right? And you have to have this kind of notebook. Yeah, it's different from the notebook you're taking notes in the classroom. Okay, that's my yeah. There's some small tricks there. When my daughter taking the SAT test.